All right. Hello, everyone, and welcome to the next talk. Tonight's talk is going to be on light and matter. Now, last week we talked about Newton's laws, the law of gravity, how motion works, which is a great physical understanding of the universe. But for most things in the universe, we can't readily go out and touch them, to go out and actually physically deal with them. We have to essentially look through telescopes and collect the light from those objects. So it's very important to have a good understanding of how light and matter interact. And that's what we're talking about tonight. Next week, we'll talk about how we collect that light through telescopes. So tonight's quote is from the Song of the Sky Loom, a Native American song. May the warp be the white light of morning. May the weft be the red light of evening. May the fringes be the falling rain. May the border be the standing rainbow. Thus weave for us a garment of brightness. All right, so how do we talk about light? So when we talk about light, we are less interested in the energy it carries and more interested in the rate at which light transfers energy. We, of course, call this power. And in science, and I think most other disciplines, we measure power in the units of watts. Now, remember last week we talked briefly about joules. Joules is the unit of energy. A watt is 1 joule per second. So here in this little table, I've got a whole list of different orders of magnitudes of wattage, all the way from a picowatt, which is the average power consumption of a human cell, that's 10 to the minus 12 watts, to just 1 watt, which is about a cell phone camera light, all the way up to one of the largest wattages we've ever measured, 3.6 times 10 to the 49 watts. Which is the power generated by our first gravitational wave detection back in 2015. So white light is the combination of all colors. As you see in this, album cover for Pink Floyd, you shoot white light through a prism, and it breaks up into the colors of the rainbow. Newton was the first person to explain that physically, showing that color is not a property of the prism, like many people thought, but actually a property of the light. He did that by taking just the red light out of the first prism and passing it through a second prism, and he only got red light out. If color was a property of the object, then then he would also get another rainbow out of that second prism, but he only got the red light. So color is a property of light. White light is the combination of all those colors, and black is what we perceive when there is no light and hence no color. Your computer screens, your TV screens, your phone screens, they all combine different colors to form white light. Typically red, green, and blue. If you're familiar with printing, like book printing, then they use cyan, magenta, yellow, and black. That's what they use. But for our purposes, white light is the combination of all colors. And light will interact with matter through 4 basic ways. So first we have emission. So you can imagine that. Imagine that as just a light bulb will emit visible light. The energy of that light comes from the electrical potential energy supplied to the light bulb from the outlets or from the power station, wherever. We also have the opposite of that, absorption. So when you place your hand near an incandescent light bulb, your hand will absorb some of the light, and that absorbed energy warms your hand. Transmission, for some forms of matter like glass or air, they'll allow the transmission of light, allowing it to pass through. So windows made of glass allow light from outside or inside at night to pass through. And then reflection and scattering. So light can bounce off matter, leading to a reflection when the bouncing is on the same general direction, like on a mirror, or scattering when the bouncing is more random, as light would bounce off, say, my cup. It's not a perfectly reflective surface. It will scatter light. So you can understand this by walking into a room. So both the sun and the lamp emit light. The lamp, as different objects are hit by the lamp's light, they'll do different things. So the mirror will reflect all the colors of visible light, allowing you to see the mirror. The chair will scatter red light, but absorb all the other colors, which is why you see it as a red chair. We have special cells in our eyes that allow us to absorb light, leading to vision. Outside, the snow will absorb some light, which helps in melting, but will scatter most light, so it looks bright. Meanwhile, that tree will scatter green light, but absorb all the other colors. And of course, if you were outside looking in, that glass window would transmit all the colors of the visible light, both from the sunlight outside in and the lamp inside out. So you see all four of those different ways of light interacting with matter throughout your daily life. It happens all around you. Now let's talk about the nature of light. So Newton had the idea that light was particles. He was one of the first people to think of that. But later experiments showed that light couldn't have been particles and must be waves. And that was the prevailing thought for much of the 1800s. Even during Newton's life, his contemporaries thought that particle light thing was a little weird idea of his. So we'll first talk about waves. And there are three basic properties of waves. So we've got a wavelength, which is the distance from one peak to the next. These are called peaks. The bottom parts are called troughs. So wavelength is distance from peak to peak, or from trough to trough, they're the same. Frequency is the number of peaks passing by any point each second. And the unit that we talk about with frequency is in hertz. So 1 hertz is 1 passing by per second. The unit for wavelength is just a normal length measurement. So nanometers or angstroms are traditionally used. We'll use nanometers. Speed also is a very important property that tells us how fast a wave's peaks or troughs are traveling, essentially telling us how fast the energy is traveling. There's also a fourth property called amplitude, so how high are the peaks and how low are the troughs. But it's less important. We won't really talk about that. So here in this little moving animation, you can see we've got a wavelength of some unit. Frequency, I don't think I measured the frequency correctly. I think it's a bit faster than about 1/10 of a hertz, but it gives you an idea of how we talk about that. To get the frequency, so just stare at that vertical line and count how many seconds it takes for one peak to pass and then the next peak to come. So all three of these properties, the reason we don't talk about amplitude is because it doesn't go into this formula, but all three of these properties are related by a very simple formula. So wavelength times frequency is equal to the speed of the wave. So remember that. That will come in handy very soon. Now, light waves, now you may be familiar with the ocean waves, and the waves of the ocean are clearly in the water. Sound waves are waves through the air. But light waves are not through something tangible. You can't like put your hand out and feel waves hitting your hand from, say, my lamp. But light waves come through electric fields and magnetic fields. So field is a really I didn't really tell you anything. It's a kind of a really intangible quantity. But scientists love to talk about field. So we talked about gravity last week. The Earth has a gravitational field where every point in space has some value for the force of gravity. So that means every point in space in this room has some value for the force of the electric field or the magnetic field. And light are electromagnetic waves. They are a combination of the electric and magnetic field. So you see in this image to the left, we've got an electric field going up and down and a magnetic field going side to side. The combination of those two is what light is. We won't get into more detail about that. I encourage you to go pick up a Physics 102 textbook if you want to read more about that. But just know that light travels through electric and magnetic fields. Importantly, all light travels through empty space at the same speed, the speed of light, which we abbreviate c, like in Einstein's famous equation, E = mc squared. The c there is the speed of light. And the speed of light is about 300,000 kilometers per second. Now, I say empty space is very important because light can go slower in other mediums. So light through water goes at a slower speed. Light through air goes at a slightly slower speed than light through empty space. But we tend to, the most important one is light through empty space, which is 300,000 kilometers per second. And so because all light travels at the same speed, that means their wavelengths and their frequencies have to balance each other. So in other words, the longer the wavelength of light, the shorter the frequency, and vice versa. The longer the frequency, the shorter the wavelength. So you can see here in these three waves I've plotted. One will have a wavelength of 1 centimeter and a frequency of 30 gigahertz. Meanwhile, if we have the wavelength, we've got to double the frequency to keep it actually physically true. So half a centimeter, double the wavelength, so 2 times 30 gigahertz is 60 gigahertz. If we quarter the wavelength to a quarter of a centimeter, then we've got to quadruple the frequency. So 4 times 30 gigahertz is 120 gigahertz. So that means that any type of light, if you know the wavelength, you then also know the frequency and vice versa. It's very, very important. It's a key fact. However, experiments later showed that Newton was sort of right, but also, confusingly, his contemporaries were also sort of right. Experiments have shown that light behaves as both a wave and a particle, what we call the particle a photon. And these photons are also characterized by wavelengths, frequencies, and speeds. This kind of wave-particle duality was a very important realization in the 1920s when quantum mechanics was just getting underway. And that quantum mechanics will come up again and again. We won't go into the gory details, but just know that things are less uncertain here. And so we can talk about things like the electromagnetic spectrum. So here's a beautiful illustration of several key facets of the electromagnetic spectrum, different types of light. So in the middle, up at the top, we have got the visible wavelengths. That's what our eyes can see. If we go bluer towards the purple end, we immediately get ultraviolet. These will have a shorter wavelength, but a higher frequency than visible light. Bluer than ultraviolet, we get into the X-rays. So once again, even shorter wavelength, even higher frequency. And we get gamma rays as we go bluer than X-rays. Those are the highest frequency, the lowest wavelengths. If we go back to visible and go redward, then we get to the infrared. So longer wavelengths, shorter frequencies. Then to the microwaves, what you use to heat up your food, heat up your hot pocket at the office. And then radio waves at the longest wavelengths at 100 meters, as long as a football field, but the lowest frequencies. You'll also notice that energy is here. Energy is proportional to frequency. So the higher the frequency, the higher the energy. So that's why visible light, we use that to see, is perfectly fine. Ultraviolet light comes from the sun. If you get too much of it, it can give you skin cancer. X-rays, even higher energy still, it can penetrate through skin and muscle, but not bone, which is why we can use it in X-ray machines of the doctor's office. And then gamma rays at even higher energies, high enough to turn Bruce Banner into Hulk. You don't want to be hit by a gamma ray. It can actually damage your DNA. Thankfully, Earth's atmosphere protects us from X-rays and gamma rays from space. If we go to the lower frequencies, we get to lower energy. So infrared, typically associated with the jiggling of atoms and molecules. So we register that as heat. Something emitting a lot of infrared will feel hot to us. And then radio waves, the weakest energy waves. We don't even notice it. Radio waves are passing through this room right now. They're emanating from my computer, but it has no effect on our bodies, unlike what some health gurus currently will tell you. It has no effect on our bodies. All it does is move some electrons in some radio antennae, so you can pick up the AM or the FM or the XM radio. Any of you still listen to radio. Down at the bottom, you can see images, examples of some sources on Earth and some cosmic sources. We detect all of these different kinds of electromagnetic waves, both here on Earth and throughout the universe. The sun obviously emits a lot of its light in the visible. Black hole accretion, as it's gobbling up nearby matter, will emit in the X-rays. There's things called gamma ray bursts, which we'll talk about much later. Planets, star formation centers, those emit in the infrared. The universe has a cosmic microwave background, as mentioned in one of the episodes of WandaVision. So if you're familiar with that show, they've mentioned the cosmic microwave background radiation. And then we also have radio galaxies. We'll get into all of that much later. But when we see all the different types of electromagnetic radiation throughout the universe. Light is everywhere, essentially. All right, so here's a question. Compared to red light, blue light has higher frequency and A, higher energy and shorter wavelength, B, higher energy and longer wavelength, or C, lower energy and shorter wavelength. So pause the video, think about your answer, and unpause when you've got an answer. All right, the correct answer is A. So remember, I just said that energy is proportional frequency. So it has higher frequency, then it's got to have higher energy. So that means C cannot be the correct answer. Now, you've got to remember that wavelength and frequency for light have to be interchanged. So red light has a higher wavelength than blue light. So that means blue light will have a shorter wavelength. Remember, blue, think about gamma rays, X-rays. Red light, think about infrared and radio waves. So that's why A is the correct answer. All right, if we're going to talk about how light interacts with matter, we also got to talk about the properties of matter. So hopefully you've heard all of this before. We'll just go over it sort of briefly. So matter, everything we see around us is made up of atoms. The idea of atoms, although incorrectly stated, was conceptualized by the Greek philosopher Democritus about 4 centuries before the Common Era. Atoms are made up of protons, neutrons, and electrons. So protons and neutrons are found in the nucleus, while electrons, quote unquote, orbit the nucleus. In chemistry classes, and even in some physics classes, the traditional view of an atom is that we've got a nucleus of the protons and neutrons, and then the electrons are on circular orbits around the nucleus, similar to the planets around the sun. Quantum mechanics says that's not technically true. This top picture is really shows you what electrons are. It's sort of just this kind of smeared out distribution of electrons. Quantum mechanics says we can't actually know where the electron is. So instead, what we see is just kind of this smeared out cloud of electrons that does sort of orbit the nucleus, but not in a traditional sense. An important property of these 3 particles is their electric charge. So protons are positively charged, neutrons are neutral, they don't have any electric charge, and electrons are negatively charged. Oh, excuse me. You might imagine, you might be asking why all the positively charged protons in the nucleus don't just repel each other. Because remember, like things repel, opposites attract. Well, it's because there's an even stronger force than the electromagnetic force in the nucleus, and that's called, creatively named, the strong force. But that holds all the protons and neutrons together in the nucleus. The electromagnetic force keeps the electrons in orbit around the nucleus. And then another law keeps them from falling into the nucleus. We won't get into that. Not yet, at least. Each chemical element contains a different number of protons. So this is its atomic number. So hydrogen has 1 proton in the nucleus, so its atomic number is 1. Helium has 2 protons in the nucleus, so it has an atomic number 2. Carbon has 6 protons in its nucleus, so it has an atomic number 6. Now, confusingly, the total number of neutrons and protons in an element's nucleus is the atomic mass number. Hydrogen doesn't have any other, just has the 1 proton, doesn't have any neutrons. So its atomic mass number and its atomic number are the same. They're both 1. Helium has 2 protons and 2 neutrons. So its atomic number is 2. Its atomic mass number is 2 plus 2, or 4. Carbon has 6 neutrons and 6 protons in its nucleus. So its atomic number is 6 for the 6 protons. Its atomic mass number is 6 plus 6, or 12. That looked like a very easy sequence. Not all elements have a 50-50 split between protons and neutrons. Uranium is something like element 92, but it can have like over 100 neutrons, 92 protons to make it uranium, but then over 100 neutrons. So don't let that, 1, 2, 6 kind of thing, don't let that distract you there. That's just for illustration. And then we can talk about isotopes. Isotopes have the same number of protons as just the normal element, but have a varying number of neutrons. So the standard carbon, if there is such a standard carbon, is carbon-12. So 6 protons and 6 neutrons. But we can add and take away some neutrons as well. So we get things like carbon-13, where we still have 6 protons to make it carbon. But we've added an extra neutron, so we have 7 neutrons. So it's carbon 6 plus 7, 13. Similarly, add 2 neutrons, and we get carbon-14. They still have the same properties as normal carbon, carbon-12, but they might not last as long as carbon-12. They might decay sooner. We'll get into that also much later. All right, and now let's just talk about phase changes of matter. So hopefully you're all familiar with the 3 normal states of matter: solid, liquid, gas. We'll run through those pretty fast. So we'll start at the bottom of this figure. We'll look at water, for example. So at low temperatures, water molecules will have a relatively low average kinetic energy. Remember, relatively low temperature, allowing them to be bound to their neighbors and form solid ice. The molecules are in this sort of crystal lattice, doesn't let any of them really move around much. And so that's why it's a solid ice. Once the molecules reach the melting point, which is 0 degrees Celsius or 32 degrees Fahrenheit, or 273 Kelvin, the bonds are broken and liquid water is formed. So there may still be bonds between a few of the molecules, but for the most part, the bonds are sort of broken. We get a liquid water. Once the molecules reach the boiling point of 100 degrees Celsius or 212 degrees Fahrenheit or 373 Kelvin, the bonds between the molecules are completely broken and a gas, water vapor, is formed. So now the molecules are still held together. We still got an oxygen combined with 2 hydrogen atoms, but those molecules are no longer controlled by each other. They're free to go wherever they want. And those are the normal, very familiar 3 phases of matter. However, at higher temperatures, the bonds inside the molecules break, which is known as molecular dissociation. This happens at temperatures of thousands of degrees. And typically temperatures of inside some stars, maybe some planets too, I'm not sure about that, but definitely inside some of the cooler stars, where now instead of an oxygen atom with 2 hydrogen atoms, water will actually break up into a hydrogen atom and then an oxygen-hydrogen combo called a hydroxyl. But the point is that molecule we know as water has been broken, has been dissociated. At tens of thousands of degrees, at even higher temperatures, collisions between the dissociated molecules will break the bonds holding the electrons to their atoms. And this is known as ionization. And so a plasma will form. This plasma will be filled of ions, just bare protons and bare electrons zooming around the place. This is commonly called, a plasma is commonly called the 4th state of matter because light interacts differently with the plasma than it does with a solid, liquid, or gas. So we tend to call this the 4th state of matter. At this temperature, definitely inside stars. Stars are made of plasma. And then depending on the element, It can be ionized more than once, leading to a fully ionized plasma, millions of degrees. So what do I mean by ionized more than once? So in water, we've got the oxygen atom. It's already been ionized, doesn't have a hydrogen attached to it. Now that oxygen atom has 6 protons, and to keep it neutral, it will have, sorry, not 6, 8 protons. To keep it neutral, have 8 electrons around it. You can singly ionize it by removing one of those electrons, but it still has 7 electrons. So you can keep ionizing it until you have truly just a bare nucleus and some electrons whizzing around. So we could talk about singly, doubly, triply ionized oxygen. We see those all over the place. In fact, my research, one of the things I use to study star formation is doubly ionized oxygen. That means an oxygen with only 6 electrons instead of all 8 of them. So we see that all over the place in the universe. The universe is very good at ionizing things. All right, so we've kind of gone through the phase changes of matter, and now we will move on to talk about light some more. So now that we understand matter, how do we get light out of the matter? How does a light bulb emit light? How does the sun emit light? What is producing that? So to produce light, objects must somehow transform energy contained in their matter into the vibrations of those electric and magnetic fields that we call light. So atoms contain energy in 3 different ways. So they possess mass energy in the amount of mc squared. Remember, that's Einstein's thing. They are also moving around. So they've got kinetic energy just because they're moving around. Note that even solids will have some kinetic energy in their atoms because they're still jiggling in place. They're not zooming around, but they're just kind of jiggling there. They'll have some kinetic energy, although a small amount. But they also contain electrical potential energy that depends on the arrangements of their electrons around their nuclei. And that's the point that we're going to talk about. So the energy stored by electrons in atoms has a very strange but important property. The electrons can only have a particular amount of energy, but not any other energies in between. So this is very weird. It's like you have a car that can only drive at either 5 miles per hour or 25 miles per hour, but none of the speeds in between. That is exactly what is happening with these electrons. These possible energies are called energy levels, and we tend to talk about them in the units of electron volts, which is just 1.6 times 10 to the minus 19 joules. Very, very small amounts, but instead of having 10 to the minus 19 joules carried around, we just call that an electron volt. So, like I said before, those electrons will orbit the nucleus, but they can only orbit at certain energies, so at certain distances away from the nucleus. So we get these different energy levels. So level 1 is typically called the ground state. It's the closest it can get into an electron to get into the nucleus. Electrons want to be in the ground state. It is the best level for electrons. If it wants to move up a level, it has to, if it wants to rise or fall from one energy level to another, it has to gain or lose the specific amount of energy between levels. So this figure is the energy level diagram for hydrogen. So we've got 1 proton and 1 electron. Now, electron's in the ground state and it wants to move up to level 2, for instance. The difference in energy between level 1, the ground state, and level 2 is 10.2 electron volts. So if it wants to move up to level 2, it has to absorb exactly 10.2 electron volts. It can't accept 5. There's nowhere for it to go. It can't accept 11. That's too much. It's sort of like Goldilocks and the 3 bears. 10.2 is just right. Now, once it's up at level 2, if it wants to move back down to level 1, it's got to release 10.2 electron volts. It can't release 5. It can't release 11, certainly. It has to release exactly 10.2 electron volts. Now, if an electron at the ground state happens to get hit by a photon carrying 13.6 electron volts, they'll be able to jump out of the atom and be ionized. That electron will have enough energy to escape the atom. So all this jumping around with exact energy levels, exact right amounts, we call this, the energy levels are quantized. This is quantum mechanics in action. This was a very bizarre result to get in the 1920s, but understanding it allows us to have all the technology we have today. So it was a very important result to understand. And these energy levels, the electron being able to jump around, either absorbing a photon to move up a level or emitting a photon to move down some number of levels, is very important to the study of astronomy in particular. So let's talk about this. So this is a beautiful, beautiful image of the solar spectrum. So at the beginning, that's what I was showing you with white light going through the prism, breaking up into the colors of the rainbow. Breaking up into the colors of the rainbow, that's a spectrum. Here you can see the colors of the rainbow. However, there are a bunch of dark spots. Some of them are just pure dark lines. Some of them have a bit of fuzz around it. And so this is what you would get if you were to take the sun's light, put it through a prism, and break it up into the colors of the rainbow. So now we got to explain, what the hell are these dark lines here? That is the job of spectroscopy. So the process of obtaining a spectrum and reading the information contained within is spectroscopy. And while displaying the information spread out in this beautiful little rainbow is very gorgeous to look at, it's not actually the most scientifically helpful way to look at things. We tend to use the more boring route of plotting it. We display the spectra. This is the exact same spectra, the sun's spectrum, as a graph that shows the amount or intensity of light at each wavelength. So we got here intensity on the vertical, wavelength in nanometers on the horizontal. And so you can easily see at which wavelengths the sun is emitting a lot or little light. So up here, there's a lot of light. The sun is emitting a lot of light over here at around 500, 600 nanometers. That's right in the visible wavelength. So that's great. Meanwhile, all the way out here in the infrared and the radio, very little light is being emitted by the sun. And we can read that immediately from graphs like this. So there are three different types of spectra. These are known as Kirchhoff's laws. Kirchhoff is a very busy guy. He also had 3 laws for electrical engineers. So he really got around with his laws. So the first type of spectrum is a continuous spectrum. This is a spectrum that spans a range of wavelengths without interruption. So how do you get one of those? Well, just from any hot light source. So a light bulb, we'll just stick with light bulb for now. So the light bulb produces light of all visible wavelengths, of all colors. As you pass it through a spectroscope, pass it through a prism, it will break up into a continuous rainbow of light. If we were to plot that on an intensity versus wavelength plot like we did before, you'd see that it's just a beautiful continuous line. There's no bumps or wiggles in it. But the intensity does vary slightly at different wavelengths. So this light bulb must be emitting more light in the orange part of the spectrum than the purple part. So that could tell us information. An emission line spectrum is caused by a thin or low density cloud of gas emitting light only at specific wavelengths, depending on its composition and temperature. So the spectrum will consist of bright emission lines. So here we've got a cloud of gas, slightly warm. It will emit light at only specific wavelengths determined by the cloud's temperature or color. We take that light, put it through a spectroscope, put it through a prism, and here's what we get. We got black. But at most wavelengths, but we see bright emission lines at specific wavelengths. If we were to plot it and not just use the rainbow, then we would also see bright peaks, upward spikes at each emission line. That is an emission line spectrum. And once again, we can see that maybe these greenish teal colored emission lines are emitting more than the red. That could tell us something about what the cloud of gas is made of or the temperature that it's at. And then finally, an absorption line spectrum is a cloud of gas that lies between us and a hot light source. That cloud of gas will then absorb specific wavelengths depending on its composition. So the spectrum will consist of dark absorption lines. So we've got a hot light source, and that light is first going to pass through a cooler cloud of gas. Doesn't matter what the temperature is, as long as it's cooler than the hot light source. We'll pass it through a spectroscope, and we'll get the continuous rainbow from the hot light source, but the cloud of gas has absorbed specific parts of that rainbow. And if we were to plot it in an intensity versus wavelength plot, we'd also see these absorption lines, these downward spikes, these dips in intensity. So this would tell us that there must be some hot thing, but then we got a cloud of gas that is absorbing certain amounts of light, certain wavelengths. That is an absorption line spectrum. So here's a question. If you heat a rock until it glows, its spectrum will be a thermal radiation spectrum, also known as a continuous spectrum, B, an absorption line spectrum, or C, an emission line spectrum. So take some time to think about your answer and come back when you got an answer. All right, the correct choice is A, a thermal radiation spectrum. So a rock, even though it might not be super hot, it's certainly not a cool gas. And it's certainly not a gas in front of another hot object. So it's not an emission or absorption line spectrum. Therefore, it must be the thing remaining, a thermal radiation spectrum. All right, so how does breaking light up into its spectrum tell us anything about the thing that's doing the light emitting? So we can deduce the composition of the thing from its light. So the atoms in any cloud of gas are constantly colliding, exchanging energy in each collision. But sometimes the collisions will transfer just the right amount of energy. Remember Goldilocks, just the right amount of energy to an electron to move it to a higher energy level. But electrons don't stay at those higher energy levels for long. So at some point they radiate away that energy as a photon of a specific wavelength. Remember, energy is proportional, H, to frequency, F. So once again, here's the energy level diagram for hydrogen. And you can see when an electron in an upper level, any upper level, jumps down to level 2, it will emit these wavelengths of light. So 656 nanometers, 486 nanometers, 434 nanometers, 410 nanometers. Similarly, if it jumps down level 1, it will emit even lower wavelengths. If it jumps down to level 3, higher wavelengths still. Scientists have given names to these groupings. So when you jump down from any higher energy level to level 2, we call that a Balmer line, named after the guy who discovered those. And here you can see hydrogen's emission line spectrum done in the laboratory, and we get the red light of hydrogen alpha, the first Balmer line at 656 nanometers. We get the bluish light of hydrogen beta at 486 nanometers, the even darker blue light of hydrogen gamma, H gamma at 434 nanometers, the more purple light of H delta at 410 nanometers, and so on and so forth. We've given names to those lines because they're very important. The other two tools I use to study star formation are H alpha and H beta. And this is the emission line. Notice here the absorption line. Those absorption lines are also at 656 nanometers, 486 nanometers, so on and so forth. They're at the same spot. That's because to absorb, to move up an energy level, you have to absorb a photon of the same energy that you would have to release to move back down. That makes sense. Basically, emission and absorption are the same process, just in different directions. So you'll get the same patterns. That's why these two lines are the same wavelength, these two lines are the same wavelength, and so on, because it's just doing the same thing in reverse. So if you take a spectrum of an interstellar cloud and you get the Balmer series of hydrogen, then you know that that cloud is then made up of hydrogen. Every single chemical element leaves their own spectral fingerprints. Moreover, different ionic species. So remember, singly ionized oxygen, doubly ionized oxygen, those will also have different spectral fingerprints. They'll all leave it. So here, If we were in a classroom, I'd hand out diffraction gratings and show like neon lights, hydrogen burning, stuff like that. You look through the diffraction grating to actually be able to see these lines, but instead we'll just have to use it like this. So up at the top, we get the Balmer lines of hydrogen. We got red to the left now, bluer to the right. We got the bright red line, H alpha, then H beta, gamma, delta, all the way there. Sodium, if you've ever had a sodium lamp, an incandescent light bulb, they're yellow because sodium emits only in the yellow and the visible. You don't see any other emission lines there. Helium, sort of similar to hydrogen, makes sense. All you got to do to get helium is add another proton and 2 neutrons. But you still get a red line, a nice yellow line, which hydrogen doesn't have, but then some bluer lines. Neon, if you've ever seen a neon light in Vegas or at your local pizza place or wherever, those open signs that some restaurants have, those tend to be very red. And that's because neon emits, has emission lines pretty much only in the red. There's no blue emission lines. Meanwhile, mercury, if you've ever had a mercury lamp, you might think those are a bit bluer than sodium lamps. And that's because mercury has emission lines there in the blue. Molecules also can have spectral fingerprints. And that is because there's generally two atoms to make a molecule. The rotation of those atoms around each other and the vibration will also create molecular bands. So this is the spectrum of a very cool star where the temperatures are cold enough that molecules can form. And you just see this thing littered with molecular bands. So here's H alpha. There's not really much of a dip or even a peak at H alpha because the star isn't hot enough to ionize hydrogen. But it is cold enough so we get all these little bumps and wiggles caused by titanium oxide or calcium hydride or vanadium oxide. We've got some iron, ionized iron there, some magnesium lines, some sodium lines. Those cool stars, really, those molecular bands really just throw havoc on people like me whose research gets bugged by them. But they're very cool for those molecular bands. Here is a very cool way of demonstrating spectra. So this is the Great Orion Nebula in the constellation of Orion up here at the top. Just a beautiful amateur image of Orion. But they pass the light through a spectrograph. So here, this is the zero order beam. We're not going to really pay attention to that and ignore all the rainbow lines. Those are from the stars around the Orion Nebula. But if you look here, you see a blue Orion Nebula and a red Orion Nebula. The red is the brightest Balmer line of hydrogen, H alpha. So we know the Orion Nebula has hydrogen. The blue is from doubly ionized oxygen. So we know that there is oxygen in the gas that makes up the Orion Nebula. We don't typically display things like this, but it's very beautiful, a very beautiful way of understanding spectra. We can also deduce the temperature of an object from the light it's emitting. So a lot of words, and I'll show you what we're talking about. So in a cloud of gas, the individual atoms or molecules are essentially independent of each other. So we get that emission and absorption spectra. But in most objects are not gas. Most objects, the atoms and molecules are not independent. They're solids, they're stuck together, or even a liquid, maybe. And so we get continuous spectra. So now consider an object that absorbs all photons that strike it and does not let photons inside it escape easily. We call this type of object a black body. Photons will bounce around randomly inside this black body, exchanging energy with the black body's atoms until all of the energies of the light inside the black body become so randomized that the object emits a continuous spectrum. Importantly, the spectrum from such an object only depends on the temperature, because the photons will end up with energies that match the kinetic energies of the black body's own atoms. So we call this radiation thermal radiation, or continuous radiation. Thermal radiation producing a continuous spectrum. So there's a lot of words. This is what it looks like. So here we've got Don't worry about the units or the numbers here, but we've got intensity on the vertical, wavelength on the horizontal. And I've got different objects at different temperatures. I've also marked off where the visible light is. So we've got a 310 Kelvin human, a 3000 Kelvin star, the sun at 5800 Kelvin, and an even hotter 15,000 Kelvin star. Now, if you were to look at this plot for a while, you hopefully would notice two things. And these are the two laws of thermal radiation. So the first one is the Stefan Boltzmann law, named after the two guys who discovered it, that each square meter of a hotter object surface emits more light at all wavelengths than a cooler object. And then Wien's law, hotter objects emit photons with a higher average energy, which means a shorter average wavelength. So here are the two laws in action. So hotter objects emit more radiation at every wavelength. So if you look at the 15,000 Kelvin star, at all points, it is more intense than, say, the sun. So at this point, it's higher than the sun. At this point, it's higher than the sun. At this point, it's higher than the sun. That is law number one. Hotter objects will emit more radiation at every wavelength. Law number two, that the peak wavelength is further to the left, further towards the blue for hotter objects, showing that hotter objects emit more of the light at a shorter wavelength. So a 310 Kelvin human emits most of its light here in the infrared. Meanwhile, a 3000 Kelvin star still is primarily in the infrared, but it will appear red to us since it has more light at the red end of the visible spectrum. The sun peaks in the visible spectrum, so it will appear yellow or white to us. We really do see it as white. Meanwhile, the 15,000 Kelvin star peaks in the ultraviolet, but we'll see it as a blue since that's in the visible spectrum, that's where it's highest. So by getting the spectrum of an object, we can then see what the temperature of that object is at any wavelength. What the temperature of the object is and how it emits light across all wavelengths. We also deduce the speed of an object from its light. So that brings in the Doppler effect. So you probably noticed the Doppler effect if you've ever been on the highway or the interstate or wherever, as emergency vehicles pass you, or if you're a fan of the Indy 500 as those race cars, or NASCAR as those cars come around the bend. You hear that? That's the Doppler effect. This is caused because sound waves are bunching up as the car comes towards you, which makes them higher pitch, and stretching out as it speeds away from you, which makes it lower pitch. You can see that illustrated in the figure at the top right. Because light is waves sometimes, the same thing can happen to light waves. So if an object is moving toward us, its light gets bunched up. So the entire spectrum is shifted towards shorter wavelengths. We call that blue shifted. If an object is moving away from us, its light gets stretched out. So its entire spectrum is shifted towards longer wavelengths. So we call that red shifted. Furthermore, the larger the shift, the faster the object is moving. So here you can see some sort of, I don't even know what element this is. It's definitely not hydrogen. But you see up at the top, the laboratory spectrum. So the object is not moving. That's what we're comparing it to. Here, the lines have moved slightly towards the red. So that object must be moving away from us. Now they move further towards the red, so it must be moving away faster than object one. Object three, compare again to the laboratory, they've been blue shifted. The object must be moving toward us, whereas object four has been even greater blue shifted. So the object must be moving toward us faster than object three. So Doppler effect applies not only to sound, but also to light. But it's important to note that the Doppler shift only tells us the part of the object's motion that is directed toward or away from us, not how fast an object is moving across our line of sight. So if star number one was moving straight along that red arrow, then the Doppler effect would tell us the full speed. Star number two is not moving away or toward from us, it's only moving across our line of sight. So the Doppler effect would tell us nothing at all. Meanwhile, star number three is moving sort of at an angle to our line of sight. So The Doppler effect would tell us part of the star speed that's away from us, this shorter dotted arrow, but not the part of the speed along our line of sight, this, across our line of sight, this longer dashed arrow. To get those longer dashed arrows and to measure the stars too, we actually have to watch them year after year as it moves across the sky. Then, if we know a distance to that star, we could translate that apparent motion on the sky to an actual physical motion in terms of speed, like kilometers per second. How the Doppler effect is very useful because it tells us not only how fast an object is moving toward or away from us, but can also reveal information about the motion within the object. So this figure kind of illustrates it beautifully. So we got star A and star B. Star A is rotating slowly. Star B is rotating faster. So that means that is star A is rotating in the clockwise direction. This part of the star's light is going to be pushed towards us. So the wavelengths are going to be kind of scrunched up. It's going to be slightly blue shifted. The light from the center isn't moving toward or away from us. Remember, it's just moving along our line of sight, so Doppler effect won't have any effect. Meanwhile, the part that's rotating away from us, the wavelengths will be stretched out, so it'll be slightly redshifted. So when we take the star spectra, we'll get something that looks like this. It won't just be a straight emissions spike. It'll be kind of smoothed out, because lights from the different parts are shifted only slightly from the center. So the red shifted part is towards the red, the blue is towards the blue. Meanwhile, star B is rotating faster. So the light coming, rotating towards us is going to be more blue shifted than star A. The light coming, rotating away from us is going to be more redshifted. So the spectral line from star A is more broad because the light from the different parts is shifted farther from the center. So we can get the speed of the whole object as well as the rotation speed of that object, which is very, very cool. So as a final test, I want you to tell me what this object is. This is its spectrum. You can see the rainbow spectrum with absorption lines and emission lines at the bottom, but also its intensity versus wavelength plot. And you can see different parts are labeled. So the spectrum that we're measuring is the full line. So we've got some emission lines in the ultraviolet, which means that this object has a hot upper atmosphere. We've got some weird shape here. The dashed line shows the thermal emission from the sun. So this thing must be absorbing blue light from the sun because there's less of it here, but reflecting red sunlight. So it must have sort of a rust-colored surface. We've got some absorption bands here in the near infrared and the far infrared. Those are caused by carbon dioxide. So it must have some carbon dioxide in the atmosphere. And then we've got a peak up here. This is the thermal emission peak in the infrared, which means that its surface temperature is about 225 Kelvin. So what object is this? I'll give you a hint. It is in the solar system. The rust-colored surface is a great choice of words. CO2 is also a key hint. So put your answer in the comments or direct message me what your answer is. And I'll tell you if you're correct. But otherwise, that concludes tonight. So we've talked about light and matter. Next week, we will talk about how we get the light from the matter through our telescopes. So thank you.